for potassium? Negative 94, correct. And what did we say is the equilibrium potential for sodium? Positive 60, okay, positive 60. So let's combine those forces, because you know on a resting neuron, right, the membrane potential is made up equally of both of these forces, okay? But we have to look at the ions that are moving. Again, we're considering sodium and potassium, but there are much more potassium channels on the membrane. And so the neuron is much more leaky or much more permeable to potassium. And so what we'll see is that potassium influences the resting membrane potential slightly more than sodium does, simply because there's more permeability for potassium. Okay, so again, just to summarize here, let's look at our chemical forces. Our chemical forces were based purely on concentrations. And if you look at the direction of those forces, again, based upon the difference in concentrations on either side, potassium wants to go out, sodium wants to come in, okay? Now, what we have here in terms of permeability is that this is not as straightforward as potassium just coming in and sodium just going out, right? We have more potassium channels, or think about it as more potassium doors, okay? And less sodium channels or less sodium doors. So, because we have potassium leaving the cell at a slower rate, but it's doing so through more channels, and we have sodium entering the cell, entering the neuron at a faster rate, but it's only doing so through one channel, we eventually approach this condition which we call steady state. Okay, and this is how we get our resting membrane potential. I'll say that again. We considered the equilibrium potential of potassium, and we found it to be negative 94 millivolts. We considered the equilibrium potential of sodium. We found it to be positive 60 millivolts. Now, these are the forces that are acting on these two ions independently. But in actuality, on a neuron, those forces have to be blurred or combined to make up the resting membrane potential. But potassium is going to be more influential on that resting membrane potential simply because we have more of a permeability to potassium movement on a neuron. Okay? I hope that's making sense. Any questions at that point? Any questions? Any questions? What questions do we have? So this may not make sense the first time you see it, but try to think about it in your mind. And if you have questions or areas where I lost you, question?
Why is it showing the chemical and electrical forces in the same direction?
Right, good question. So basically we have both of the forces are going inside. Simply because we have a negative environment in here, sodium is positively charged, right? We said that attraction of the opposite charges is going to want to bring sodium into the cell, right? We're no longer considering that hypothetical cell, so don't get confused where we had sodium moving in the opposite direction. Okay, this is what an actual cell looks like, and this is when we blur those two forces together or combine them. Okay, so we have sodium moving in, again, a faster force, greater magnitude of that ECDF, because both of them are going in the same direction. But there's only one sodium door, so to speak, right? Or in decreased permeability. Whereas we have opposing forces for potassium, but there are many potassium doors, or there's increased permeability for potassium. And so what we see is that potassium flows out slowly, whereas sodium flows in quickly or fast. Okay, I really want that to sink in and to make sense. Potassium flows out slowly. Remember we said if we had forces in the opposite direction, we subtract the weaker force from the stronger force to get our magnitude. And so because these forces are going in different directions, it's going to be a smaller magnitude, okay? So it's going to go out slowly in terms of the strength of that force, the strength of that movement. Whereas sodium has both forces going in the same way, so they're pretty much going to amplify. Okay, so we have a stronger force in terms of the magnitude or the strength of that movement, simply because they're going in the same direction, right? We add those two forces together. And so this is what a neuron looks like at rest, and this is how we get to the resting membrane potential. Okay? Again, the movement of these ions approaches what we call steady state. And steady state basically means that the inflow of sodium is balanced by the outflow of potassium. And I really want you to understand why that is the case. Because of the permeability of potassium. So potassium is moving out slower, but it's doing so through more channels, whereas sodium is moving in faster, but it's doing so through less channels. And those two opposing phenomena balance each other out in this condition called steady state. So this is what a neuron looks like, absolutely chilling out, doing absolutely nothing. This is at -70 in terms of its membrane potential. Alrighty? Any questions? So this is how we establish the resting membrane potential. This is going to be very important in understanding how we fire an action potential. Okay? A cell basically manipulates its channels, it manipulates its ion channels to change the membrane potential. And if we change that membrane potential, we can fire an action potential, which is this bolt of electrical energy that rushes through a neuron and allows neurons to speak to each other at the synapse. Okay? So very important sort of underlying information about how neurons work. And as we speak about the resting membrane potential and as we speak about the synapse, it's very important that you understand these concepts. Okay? If you are unfamiliar or you don't remember the CDF and the EDF and the ECDF, please go back to that material and review it. Okay? All right, so we established the resting membrane potential. It's -70 millivolts. That's what a neuron looks like at rest, not excited. And so how do we maintain it? So we've established it at -70. How do we prevent it from waxing and waning? How do we maintain the resting membrane potential? We spoke about two features on the cell. And again, I keep saying cell, but we're focused on a neuron here, not another cell. So we talked about two features on the membrane of a cell. Can anyone remember that we said help to maintain those relative ion concentrations? The sodium-potassium pump. So the sodium-potassium pump, very, 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 very crucial in maintaining these relative ion concentrations. That pump is the whole reason that we can absorb food, that we can use the bathroom, that we can generate urine. Very, very important, important feature, not only in humans, but in other life forms as well, the sodium-potassium pump. And a lot of processes rely on this pump. So maintaining the resting membrane potential is done by the sodium-potassium pump, but also by these leak channels that we talked about. So we have the pump basically bringing potassium in, potassium leaks out, okay? Likewise, the pump is pumping sodium out, sodium leaks right back in. Okay, and so this combination of what we call the pump leak system is pumping an ion in against its concentration gradient, and it leaks in the other way passively along its concentration gradient. And so having that phenomenon, that cyclical movement of ions, is what maintains that -70 millivolts and prevents it from waxing and waning. Because although we're moving ions, there's no net accumulation of ions in either side. And so the inside stays negative unless we excite it, right? We'll talk about that next week. And the outside stays positive, again, unless we excite this neuron. All right. Any questions on that so far? Any questions? So when we look at this sort of illustration here, we can compare what the cell looks like at rest to the equilibrium potential of sodium and the equilibrium potential of potassium. We can sort of compare where that resting membrane potential falls. But what we can also see being illustrated in this, this image here is that there's a greater difference between the equilibrium potential of sodium and the resting membrane potential. There's a smaller difference between the equilibrium potential of potassium and the resting membrane potential. What is creating that small difference between potassium's equilibrium potential and the resting membrane potential. Why is this more like potassium's equilibrium potential? Why does the resting membrane potential look more like the equilibrium potential? We kind of mentioned it. Why is it more influential on the RMP? All right, so because we have more potassium channels on the neuron is more leaky to potassium, the neuron is more permeable to potassium. The movement of potassium will more influence the resting membrane potential. This also indicates to us the force to move potassium, right? And we said that those forces were in opposite directions, and so the magnitude wasn't that big, it was very small. Whereas for sodium, sodium had a very big force to get into the cell. And we can see that reflected by its difference from the membrane potential. Alrighty. Okay. So let's just go over some summarizing points here. So if the membrane potential is not at equilibrium for an ion, okay, the electrochemical force is not zero, meaning that particles are moving. Alrighty. Now the net force to act to move the ions across the membrane in the direction that favors it being at equilibrium. And let's jump back to this. Let's jump back to this. The net force acting on sodium is going to want to bring it into the cell, hence a positive equilibrium potential. The net force acting on potassium is going in the opposite direction. It's going to want to take it out of the cell, hence that negative equilibrium potential. Let's look at that third statement here. The strength of the net force increases the further away from the membrane potential the equilibrium potential is. All right, I'll say that again. The strength of the net force increases the farther away we are from the membrane potential. So the farther away the equilibrium potential is from the membrane potential, the bigger the force, the bigger the strength of that force. And again, we can see that here. Sodium's equilibrium potential is very far from the resting membrane potential. And we have that much stronger, bigger force for sodium to rush into the cell. Potassium's equilibrium potential is not very far from the resting membrane potential. So we had a weaker, more trickling force that wanted to sort of slowly push potassium out of the cell. Not as strong as the strength that is trying to move sodium. Okay? All right, so again, reviewing here, we talked about the resting membrane potential to be negative 70 millivolts. We spoke about potassium's equilibrium potential to be negative 94. And so there's a difference of 24 millivolts, right? Comparing those two potentials. And that basically tells us, summarizing here, that the electrical force is into the cell and it's lower or slower, whereas the chemical force is out of the cell and it's higher or stronger. And so the general direction of the ECDF is going to be in the direction of the stronger force. So potassium is going to want to go out of the cell because of its bigger, stronger CDF, okay? And so the net force will be weak, right? Because of that difference in the direction, we have to subtract those forces, but we have many more channels or many more doors for potassium, okay? And likewise, let's look at sodium. Again, we have our resting at negative 70. Sodium's equilibrium potential is at positive 60, so very far away, right? And again, that difference is indicating to us the strength with which sodium is trying to get into the cell. Okay, that difference from the resting membrane potential. And so we have a very large difference here of 130 millivolts. That tells us that there's an electrical force into the cell, also an chemical force into the cell. The forces are in the same direction, so we add them and get 130, which is the magnitude of that force now. It's much stronger in that same direction into the cell. So we have a strong net force, and again, when we say net force, we're simply mentioning the ECDF, right? Combining electrical and chemical forces. But we have a lower permeability simply because we have less sodium channels. So that really equals out the movement of sodium and potassium at that negative 70, which is our resting membrane potential. All right? Any questions? Any questions here? Any questions? Mm-hmm.
So is chemical and electrical forces always opposite?
They aren't always opposite. No. We have to look at the concentration gradients to see the direction of chemical. And then we think about the charge on the cell, okay, after the movement of those ions along their concentration gradient. So think about it sequentially. Think about the CDF, think about the EDF, then add them, okay? So this is basically an overview of what we have in the cell, sort of putting all the players that we talked about, the leak channels, the pump channels, our relative concentration gradient, and what our overall membrane potential looks like, okay? So small sodium leak at rest, which is a high force and a low permeability, okay? Whereas we have a small potassium leak at rest, which is a low force and a high permeability. Like think about those doors or those channels. So the sodium pump is what is maintaining all of this. That's sort of the third factor here we talked about. That is returning these concentrations to their normal state. If we didn't have that sodium potassium pump, think about it in your mind. If it wasn't there, we would not maintain this -70, no way, okay? Because you would have ions moving in the opposite direction but not being pumped, or ions moving in one direction but not being pumped in the opposite direction. So this pump, along with the leak channels, that pump leak system is crucial to keeping this at rest, keeping this -70 going, all right? Okay. All right, I just wanted to end off on this slide. This is sort of a segue into what we'll talk about on Monday. We'll speak about how we can manipulate this membrane potential. So we talked today extensively about how we figured out this baseline, how we got to that -70. And next week, we'll talk about how we can manipulate some channels on this cell and actually influence the membrane potential such that we can fire an action potential. This is how neurons fire that jolt of energy, which allows them to talk to each other, to innervate muscle,